Welcome back, folks. In today's class, I'll talk about a new topic, that is the oscillatory motion, and then we'll talk about the spring force and the spring energy. So that'll be the topic for the day. Now, what is an oscillatory motion? So a motion which repeats itself over a regular period of time. So for example, if any object is moving in a circular direction, so this once you is trying to move any object in a circular direction, it means that motion is being repeated over a period of time. For example, the motion of a fan. Fan circulates. So it's just same motion, repeated motion. Now, with regards to the repeated motion, there are two terminologies which we need to know. One is the time, and another is frequency. Frequency. Time is also called time period. Time period means the time taken to complete one cycle. Time taken to complete one cycle. That is the time period. Just let me check whether I'm recording this lecture or not. Yes, so I am. So that is the time period. Now, if I have to visualize this, so this is from where I started, and this is again at the same point, this is where I ended. Whatever time this journey will take, that's called time period. It can be 1 second, it can be 10 seconds, it can be 1 year, 2 year, 3 year, 10 years also. So that's the time period. Frequency means number of cycle in 1 second. That's frequency. And the unit of frequency is hertz. Unit of time period is seconds. Unit of time period is seconds, and frequency it is hertz. Now, number of cycles in 1 second. So if I start from here, it can take maybe more than 1 second. It can take 2 seconds, or maybe it can take half a second also. So frequency means number of cycles the object will take to the number of cycles the object will complete in 1 second. So for example, if I use the term frequency is 5 hertz, it means the object has covered 5 cycles in 1 second. The another unit can be revolutions per second, 5 rps, revolutions per second. Sometimes you might be given in the questions revolutions per minute. So you have to convert minute into seconds. So we need to pay attention to those things also in the question. So hopefully you understood this motion. This was specific example of the circular motion. And then another type of oscillatory motion can be a to and fro motion. For example, if I talk about a spring, so this is a spring which is in its natural state. So once you push the spring in the forward direction and stretch it, and then what's the natural tendency of the spring is? Natural tendency of the spring is to move back to its original position, to come back to here. And in doing so, first of all, let's say there is a mass connected to this spring. So I'm going to redraw a spring. So this is a spring and there is a mass attached to it. Now I move this mass in the forward direction to a distance delta x. So the spring is stretched and then I leave it. So what's going to happen? This mass will start moving in the opposite direction, and then because this is a mass, so there will be inertia associated with this, and that will try to compress the spring also. So let's say the spring, this is the next stage. Once you release this mass, so it the spring gets compressed and it moves to a distance, let's say delta x on this side also. I'm just assuming these two distances are equal just for the sake of simplicity. Then so what's happening is you are stretching, then it is again trying to regain its original position, but because of the momentum it compresses. Then because of this compression it will again try to push it in the opposite direction. So that's also a to and fro motion. You know, the the cycle is being repeated in this case. So this can also be taken as an example of oscillatory motion. Means we are trying to find out the continuous cycles. Any motion which repeats the continuous cycles can be put under the oscillatory motion. Now, let's talk about the forces on this kind of a system, because that's what we said, that we're going to talk about the spring force and spring energy too. So let's say this is a spring, and now and there is a mass attached to it. You stretch it in a forward direction, it reaches to this position. This is the mass. Now at this location, when the spring is stretched, and the distance moved is delta x, when the spring is stretched, there will be some sort of a restoring force which will be generated in the spring, and that restoring force is denoted by term Fr. Fr, formula for finding the restoring force, is equal to negative kx. Now please don't confuse yourself when you see the different books. Sometimes you are also given spring force F equal to kx, and sometimes it will be given negative kx. So negative means it's just a restoring force. Fs is the spring force, the force you actually applied to move it in the forward direction. This is a forward force, so we took it as positive, and this is a negative because restoring force always acts in the opposite direction to the applied force. So this was the equilibrium condition. And now at this location, I would like you to pause the video and think about it. What will be the amount of restoring force which will be generated? So welcome back, guys. Now, I guess you guys might have guessed it now. So at this point, restoring force will be maximum, because you've applied whatever stretching force you could have applied, or the spring force, shall I say. And now this will be equal to this. The only difference is it is restoring forces in the opposite direction. Now restoring force is maximum. So if force is maximum, then acceleration value will be maximum also, but this will be in the opposite direction. Once this, and then what is the velocity at this point? So velocity at this point will be zero, because you stretched it in this direction and all the opposite forces have piled up into this mass and spring system. So velocity is zero. It is not moving. You just stretched it. Now, once you release it, then the force will cause the mass to move. And this mass will start moving in the opposite direction. So it will start generating some velocity. Once it reaches to its equilibrium position or the neutral position where it was. Okay, so this I'm trying to draw the neutral position. Here velocity will be the maximum, because all the restoring force which the spring system has generated at this point, that has converted into the velocity now. Now because of this velocity, and there is inertia, mass is there, so that will try to push it. So once it goes beyond the neutral position, it will start compressing the spring. So once the compression will start, velocity will also start reducing. And again, what's going to happen? All the force, all the velocity will again get converted into the spring force. So it will look something like this at this point. So here there will be restoring force generated, but this time around restoring force will be in this direction, in the forward direction, and acceleration will also be max. Restoring force will be max, and I'm assuming that there is no loss because of friction in all these cases. So because a thing can come to your mind that okay, over a period of time it will slow down. It will only slow down if there is frictional losses. Yes, in real life there are frictional losses, but in this case we are assuming there are no frictional losses which are occurring. And then velocity at this point will be zero at the maximum compression. So from here, we concluded one formula which we will use later on. Force equal to restoring force equal to negative kx. Okay. Now, if I move this horizontal spring system into the vertical spring system, so if it looks like this, now there's a mass attached to it. Now this mass, what force is acting onto this one? There is a gravitational force Fg which is acting onto this one. But as soon as gravity is trying to pull it in the downward direction, or you apply certain force in the downward direction, there will be a restoring force which is going to get generated. So assume there is no mass, and this is the natural tendency of the spring right now. That's the neutral position. Now I attach a mass system to this one. Here there's a mass which is being attached. So naturally there will be a gravitational force in the downward direction, which is equal to mg, an equal amount of restoring force which will be generated in the spring mass system. So I can write an equation for this one. So in the vertical system, I can write Fr, Fr restoring force is equal to mg. So restoring force in this case is acting upward direction. So I can write it as uh, kx positive, and mg, pardon me, is acting in the downward direction. So thus you can say, you can argue that why I haven't taken it in the negative direction. So I'll show you why I haven't. So the real equation is net force is equal to, what are the two forces, Fr and Fg. Fr is positive acting upward minus Fg. So net force is zero because it's balanced. So we are doing, or we are balancing these forces. So net force is zero, and which is equal to Fr minus Fg. Fg is going to go on the other side, becomes positive. So that's why I wrote it as Fr equal to mg, or I can write here first of all as Fg, which is equal to mg. So hopefully you understood the concept of balancing of the spring forces when the springs are in the vertical direction. Now with this, I'll also talk about another concept, that is the concept of spring energy. Now in the spring energy concept, so again, I'll go back to the horizontal spring mass system diagram. So this is how the spring mass system is in the in its equilibrium position or in its neutral position. Now you apply certain force. With force, I can, if I'm talking about the energy, so I can use the term now energy. I applied certain energy to move it in the forward direction. So all that energy will be stored to move this mass in the forward direction. So at this point, energy value will be maximum. The maximum amount of energy will be stored here, and velocity here will be zero because it's just not moving. You've stored the maximum amount of energy which you could have. And this, what is this energy? This energy maximum, this is stored in form of EPE, spring energy, or spring potential energy also you can call it as. Okay, because remember, if you can recall from the previous classes, mechanical energy is sum of two energy, potential energy plus EKE, and then the potential energy, this is the spring potential energy, that's what it is stored. And then there is kinetic energy also, but at this location, because the velocity is zero, so EKE will be equal to zero at this location. Now you can, again, we can draw another diagram and we can find out at the equilibrium position what will be the condition. So once you release it, it will start moving in the opposite direction. At this location, EKE will be maximum and EPE will be equal to zero. So basically the mechanical energy concept which we are using, that mechanical energy remains constant throughout its journey, but here potential energy will be maximum. At this location, kinetic energy will be maximum. I'm going to mark it as location 1 and this one as location 2. So E mechanical equal to EPE plus EKE at, this is at location 1 and this is at EM location 2, EPE plus EKE, I'll mark it as L, L2, L2, L1, L1. At location 1, which is this one, kinetic energy is 0, so mechanical energy is same as potential energy. At location 2, the mechanical energy is equal to kinetic energy, potential energy is 0. So, and mechanical energy remains constant because we are assuming no losses in this question. Now, based on this, I can equate them, and we can find out the speed with which it will move when it reaches here or at any point. So this potential energy is equal to half kx. That's the spring energy also. And then the kinetic energy is equal to EKE, which is half mv square. Why we have compared them? Because we know that energy mechanical at location 1 is equal to energy mechanical at location 2. They both are same. And now from here I can find out the uh, value of the speed with which it is moving, kx square divided by m, and I can square root the whole thing, kx square divided by m equal to speed. Now it will be x square root of km equal to v. Now if you see some of the books, they rather than writing x, they write it as a. A is just a symbol for maximum displacement it can have. So this is if this is maximum, delta x max, so that's what we change into a. Okay, so a k upon m equal to v, and that will give me max velocity also. This is more generalized formula. So hopefully you understood the concepts of spring energy. Now I'll see you with some more video lectures and some math problems in another class. Till then, goodbye.